Hi everyone, hope you are all doing well and safe. Welcome to the practical course of Linear Control System. Here's your lab instructor Nashitah Alwaz. Agenda of this experiment includes 7 different sections: lab objective, equipment needed for the experimentation, theoretical background, software implementation, results and discussion part, conclusion, and the task assigned. The title of today's experiment is to identify the location of poles using Routh Hurwitz criterion. Equipment needed for the experimentation is LabVIEW software installed on the personal computer. Firstly, we have to look at the theoretical background of this experiment. If we talk about the requirements for the designing of a control system, then there are 3 parameters: transient response, stability, and the steady state error. As we have already know that transient response is the variation of output response during the time it takes to reach its final value, and steady state error is basically the minor difference between set point and output. We have not yet studied about the stability of the system specifically. Stability is the most important system specification. If a system is unstable, transient response and steady state errors are moot points. An unstable system cannot be designed for a specific transient response or steady state error requirements. Then what is stability? There are many definitions for stability depending upon the kind of system or the other point of view. We can control the output of a system if the steady state response consists only the forced response, but the total response of the system is the summation of forced response and the natural response, as we can see in the slide. The forced response is what the system does with the input turned on but with the initial conditions set to 0. The natural response is what the system does including the initial conditions but with the input suppressed. So if we talk about the definition of stability, then according to natural response, stability can be defined as a system is stable if every bounded input yields a bounded output. A system is unstable if any bounded input yields an unbounded output. So in these graphs we can see that a system is said to be stable if for a bounded disturbing input signal the output vanishes ultimately as t approaches infinity. At start we have some damped oscillation, but after that system is stable. In the first picture, a system is unstable in the second picture if for a bounded disturbing input the output is of infinite amplitude or frequency. According to the linear time invariant systems, stable system, unstable system and marginally stable systems can be defined as if the natural response approaches 0 as time approaches infinity, then the system is called stable system. If the natural response approaches infinity as the time approaches infinity, then the system is called unstable system. If the natural response neither decays nor grows but remains constant and oscillate, then the system is called marginally stable system. Third method for defining the stability of a control system is transfer function. As we know that transfer function is the ratio of Laplace transform of the output to the Laplace transform of the input by assuming all initial conditions to 0. Here we have the general representation of the transfer function of the system. The roots of denominator polynomial of a transfer function are called poles. The roots of numerator polynomial of a transfer function are called zeros. Pole is also defined as the frequency at which the system becomes infinite. Zero can be defined as the frequency at which system becomes zero. So the poles and zeros of the system are plotted in S-plane as we can see in the slide to check the stability of the system. How do we determine if a system is stable or not stable? If the roots of the characteristic equation lie on the left half of the S-plane, then the system is known as stable system. If the roots of the system lie on the imaginary axis of the S-plane, then the system is called as marginally stable system. If the roots of the system lie on the right half of the S-plane, then the system is known as unstable system. A necessary and sufficient condition for a feedback system to be stable is that all the poles of the system transfer function have negative real parts. A question is here, is it really possible and feasible for us to calculate roots of every kind of higher order characteristic equation? Answer is no, it is not really possible. Then what is the solution of this problem? Solution is Routh Hurwitz criteria, the basic theme of this experiment. In this experiment, we will learn a method that yields stability information without the need to solve for closed loop system poles. Using this method, we can tell how many closed loop system poles are in the left half plane, in the right half plane, and on the imaginary axis. We can find the number of poles in each section of the S-plane, but we cannot find their coordinates. This method is called the Routh Hurwitz criteria for stability. Routh Hurwitz criteria states that the number of roots of characteristic equation with positive real part is equal to the number of changes in sign of the first column of the root array. You might wonder why we study the Routh Hurwitz criteria when modern calculators and computers can tell us the exact location of system poles. The power of this method lies in design rather than analysis. For example, if you have an unknown parameter in the denominator of a transfer function, it is difficult to determine via calculator the range of this parameter to yield stability. You would probably rely on trial and error to answer the stability question. Later on in the experimental work, we will see that the Routh Hurwitz criteria can yield a closed loop form expression for the range of unknown parameter. Routh Hurwitz criterion basically includes two major steps. Step first is generation a data table called a root table. Step 2 is the interpretation the root table to tell how many closed loop system poles are in the left half plane, in the right half plane, and on the imaginary axis. So now moving towards the mathematical example of Routh Hurwitz criteria. Firstly, we have to look at the equivalent closed loop transfer function. Since we are interested in the system pole, we focus on our attention on the denominator of the transfer function. Firstly, we will create the root table. Begin by labeling the rows with the power of s from the highest power of the denominator of closed loop transfer function to the lowest power s raised to power 0. Next, start with the coefficient of highest power of s in the denominator and list horizontally in the first row every other coefficient. In the next row, list horizontally starting with the next highest power s square, right there x square, every coefficient that was skipped in the first row. So in the current experiment, we have this type of transfer function, and ds is basically, denominator is basically s cube plus s square plus 2s plus 24. So how we can arrange this equation in our root table? Firstly, we have to generate the root table based on 4 rows and 1 column, basically 2 columns. In first column, we will place s cube and place the equation of 1, skip this element, basically s square element, and put 2s base element, then 24 skip, and there is no further any numeric value, so I will place the 0 right there. In the next row, I will write down s2. So skip this element and start with s2. The coefficient of s2 is basically 1, so write down 1 right there. After this, skip this value and put 24 right there. After this, there is no element, no digit, so write down 0 after this. The remaining entries are filled like that. Each entry is a negative determinant of entries in the previous 2 rows divided by the entry in the first column directly above the calculated row. The left-hand column of the determinant is always the first column of the previous 2 rows, and the right-hand column is the element of the column above to the right. So in the current experiment, basically how we can write down minus 22 by taking the negative determinant of this column of these 2 rows, 1, 1, and after this 2 and 24, 2 and 24. So divide this block basically by 1. The first and basically the second row and the first column digit 1. So answer is minus 22. For the next basically column, we will take the negative determinant of this column 1 and 1 and this column 0 and 0 and divide this determinant again by this digit 1. So B2 is equals to 0. After taking the determinant and division, we have the value 0. So I will write down 0 right there. After this, how we can write down the 24 digit in the next row? By taking the determinant of 1, 24, negative determinant of 1, 24, then negative 22 and 0 and 0, and then to be divided by basically this digit minus 22. So we have the value of 24. So here basically 2 sign changes occur. Positive, positive, no sign change occur. 1 to minus 22, 1 sign change occur. And from minus 22, 24, we have 1 sign change occur again. So in this example, we have 2 times sign change. So it means that we have 2 poles in our right plane. So it means our experiment, basically example is unstable system. Means this transfer function is unstable network. So here we have another example based on unknown variable transfer function. So we have to check the stability of this network. So moving towards the Routh table, put s cube, s2, s and s0 value in the table. S cube has 1 coefficient, so I will write down 1 in the first row. After this, skip 2, then put 4 as we have next element 4. So in the next row means as a square row, skip this value and put 2 right there. After this, skip this value and write down k in the second row. Then I will take the negative determinant of this whole elements and divide the negative determinant by this digit 2. So if we take 8 minus k greater than 0, so k is basically less than 8. If we increase the value of 8, then our poles shift towards the right half plane, means our system becomes unstable. So now if we talk about the stability conditions of the Routh Hurwitz criteria, then the number of roots in the open right half plane is equal to the number of sign changes in the first column of root array. As we can see the root table in the slide, if any sign change occur in the first column of root table, then our poles move towards the right half plane. If the requirements are met, we still must investigate the system further to determine the stability of the system. If we talk about the advantages of this Routh Hurwitz criteria, then we have major 3 advantages. By the help of this Routh Hurwitz criteria, we can find the stability of the system without solving the equation. By the help of this method, we can easily determine the relative stability of the network. With the help of this method, we can determine the range of unknown parameter k for the stability of the system. Along the advantages of Routh Hurwitz criteria, there are some disadvantages of this method. So this method basically applicable only for our linear system. It does not provide the exact location of poles on the right and left half of the S-plane. In case of the characteristic equation, it is valid only for real coefficients. Moving towards the software implementation of this experiment, as we know that LabVIEW software has 2 main windows, front panel and the block diagram. For the creation of the functionality of any program, we have to move towards the block diagram of the LabVIEW software. To create any process continuously, we will use loop in any programming language. In this experiment, we will use for loop. For loop basically executes sub-diagram n times, where n is the value y to the count n terminal. If we talk about n in our current experiment, then n is basically the number from which we are going to run our truth table. The iteration terminal provides the current loop iteration count, which basically ranges from 0 to n minus 1. So if we talk about the iteration block in our current experiment, then I basically shows the current row in the root table. You can find out this for loop block on the function palette in the structure block of the LabVIEW software. Next icon is polynomial roots, which is basically used to find the roots of any polynomial presented on the Routh Hurwitz table. Right click on the plot diagram of LabVIEW, function palette will be open, then move towards the mathematics, then move towards the polynomial roots. Pick it and place it on the block diagram of LabVIEW software, as you can see this in the slide. Next block is complex to real imaginary function. This block breaks a complex number into its rectangular components. Find out this block by right clicking on the block diagram of LabVIEW software. Function palette will be open, then move towards the numeric, then move towards the complex block, and you will find out the icon of complex to real imaginary function. Pick it and place it on the block diagram of LabVIEW software. Build array basically concatenates multiple arrays or appends element to an n-dimensional array. You can find out this block by right clicking on the block diagram of LabVIEW software, then function palette will be open, then click on the array block. Here you will find out the build array icon. Pick it and place it and concatenates multiple arrays, as we are going to use this array on the block diagram in the current experiment for the concatenation of two polynomials. Build XY graph express basically formats data to be displayed on the XY graph. You can find out this block by right clicking on the front panel of the LabVIEW software, then control palette will be open, then move towards the graph and then build XY graph express. Pick it and place it on the front panel of the LabVIEW software. So moving towards the software implementation of this experiment. Here we are going to check the stability of the unknown variable based transfer function through Routh Hurwitz criteria. As we have seen one example in the previous slide for the determination of the stability of unknown variable k-based transfer function. So for the software implementation, we will proceed the same example and check the same system stability on LabVIEW software. As we know that LabVIEW has two main windows, block diagram and the front panel. So for the creation of the functionality of program, we have to move towards the block diagram of the LabVIEW software. To continue any process in any programming language, normally loop has been used. So in the current experiment, we are going to use for loop. So right click on the block diagram of LabVIEW software. So function palette will be open, then move towards the structure, then move towards the for loop. Pick it and place it on the window of LabVIEW software. For loop has basically two main elements, and terminal and the iteration block. And terminal is basically the number we are going to run our truth table. I is basically the iteration, means the current row in the root table. As we have already seen that each entry is determinant of entries in the previous two rows divided by the entry in the first column directly above the calculated row. So here in the current experiment, we are going to take n as 40 and divide this iteration block by 2, because in the first row we have element 2. So we will take the icon of division by right clicking on the block diagram. Function palette will be open, then move towards the numeric, then pick the division block from this window, place it on the block diagram, then right click on the division 1 block, create constant and put 2 right there. After this, we have to click I terminal block basically by the one terminal of division. After this, we will basically we will perform this summation of two arrays. Two arrays mean current iteration and the coming polynomial based iteration. So for this, we will take the icon of build array. Right click on the block diagram, moving towards the array block in the function palette, then moving towards the build array. Expand it 2 times because here we have 2 arrays. Right click on it, then choose the icon of concatenate input, because this is the major part of specification of the build array. So here we are basically concatenating 2 arrays, the current iteration and the next coming iteration, polynomial based iteration. So concatenate input will be selected. Select build array and basically connect division block with the build array block. Right click on the other element of the build array, create, control, rename it as px. After this, we will basically connect the icon of polynomial roots, because these terms are going to generate the roots. So for the determination of roots, specific roots, we have to connect the polynomial root space icon. So right click, function palette will be open, then move towards the basically mathematics block, then moving towards the polynomial, then pick the icon of polyroots, pick it and place it on the window, and after this we will connect the icon of complex to polar, complex to real imaginary, because we are going to convert every coming polynomial roots in the form of xy numbers. So for this, right click on the block diagram, moving towards the numeric block, then moving towards the complex subplot, then moving towards the complex to real imaginary. After this, basically we will connect the polynomial roots with the complex to imaginary parts. So now it's time to connect the express xy graph. All input and output blocks will be connected on the front panel of the LabVIEW software. So moving towards the front panel of the LabVIEW software, right click on the front panel, then click on graph, then express xy graph, place it on the window of LabVIEW software front panel, then move towards the block diagram. Here we have the built array xy graph already presented. So now connect the real and imaginary parts with the x and y input of built xy graph. After this, we will move towards the front panel. Here we will basically put the polynomial values as we have seen in the equation. We have polynomial value 4, 2 and 1. So run or VI, and here we have the representation of poles on the express xy graph. To analyze the result of this experiment, we have to basically move towards the build xy graph or express xy graph of the front panel of the LabVIEW software. So right click on the xy graph and move towards the optional plane, then click on S plane for the proper representation of poles, and basically deselect the Cartesian coordinate because we have to clear the representation of poles. So optional plane and deselect show Cartesian lines. So here we have the proper xy graph of this experiment. As we can see, poles are properly on the left hand side of the plane. Here we have the pole, here we have the pole, here we have the pole. Means all the poles on the left hand side of the plane. So our system is properly, completely stable, as we can see in the graph. So from this experiment, we have learned that stability is based on a natural response that decays to zero as time approaches infinity. The Routh Hurwitz criteria lets us find out how many poles are in each section of the S-plane without giving us the coordinates of the poles. Just knowing that there are poles in the right half plane is enough to determine that a system is unstable. Under certain limited conditions, it is necessary to have the information of the coordinates of the poles. Tasks assigned for this experiment are listed in this slide. You have to complete these tasks before the commencement of your next week lab. Write down your experiments in your notebooks and share the scanned copy of your work with me through Microsoft Teams. This is all from my side. You are welcome to ask any question related to this topic. Thank you very much for listening to me. Good luck. Allah Hafiz.